So now let's introduce the idea of complex impedance, which will make our analysis of time-dependent circuits even simpler. So let's just consider for now an isolated capacitor. We'll have some current flowing through it, which is a function of time, and some voltage across it, which is a function of time. And let's assume we're at the sinusoidal steady state. So we know the frequency, and it's just this sort of pure sine wave. So rather than using sines and cosines, I'm going to represent my voltage as some complex number v times e to the j omega t, and my current, likewise, I'm going to represent as some complex amplitude I times e to the j omega t. So again, this and this are both complex numbers. So our fundamental relationship for the capacitor is that the current is proportional to the time derivative of the voltage. So I can simply plug in my assumed forms for the voltage and the current. Taking the derivative of the voltage is quite easy, and my e to the j omega t's would cancel out, so I have just a simple relationship between the voltage and the current given with this sort of complex relationship. So let me define the quantity. I take the ratio of the voltage and the current as the impedance, which will give the symbol Z. And so if I just simply plug in my relations for the voltage and the current, I get this. Those things cross out, so all I have to do is take the ratio of the complex amplitudes of the voltage and the current, but I have a relationship between those, which is where I is just given by this piece here, where the V's will cancel out. And so what that leaves me with is my complex impedance is nothing 1 over j omega c. And so my impedance is kind of like a resistance, right? Because it's voltage over current. But now it's a frequency dependent thing and it's complex. So it seems maybe a little bit weird, but it's extremely useful. Now let me show you how it's useful. So it's useful because if I have 3 impedances in series, say, I can represent that equivalently as a single impedance where I do Z1 plus Z2 plus Z3. So they simply add up. I can take 3 impedances in parallel and they act as a single impedance effectively like this. And so the short answer is that impedances are just like resistors. And so if I ever have a resistor in a circuit, its impedance is nothing more than the resistance R, because resistance is voltage over current, and for a resistor there's no phase. It's just the instantaneous relationship between voltage and current, just given by the resistance R. For a capacitor, we saw that the impedance is 1 over j omega c. And so the trick to analyzing circuits with the resistors and capacitors is to just replace everything with an impedance, analyze it though it's a resistor, and then sort of add in the appropriate impedance at the end, be it resistance or 1 over j omega c. So now let's use this impedance idea to analyze this same circuit that we have analyzed already. So rather than drawing it as a resistor and capacitor in series, I'm going to draw it as an impedance Z1 and impedance Z2 in series, and I'm going to look at what the voltage is here in the middle. Now we can analyze this again just as these were resistors. So the current going through these 2 impedances is given by Vn minus 0 divided by the total impedance, Z1 plus Z2, equals to the same current, which is just flowing through this one, V out minus 0 divided by Z2, or V out over Vn is given nothing more as Z2 divided by Z1 plus Z2. And again, this is just the voltage divider, so we could have just written this law down right from the beginning if we remembered it. And again, now all I got to do is plug in what my impedances are. So Z2 is a capacitor, so it's 1 over j omega c. Z1 is a resistor, so it's R. Z2 is a capacitor, 1 over j omega c. And so now we can write that V out divided by Vn, just by multiplying through by j omega c, gives me the exact same result that we got before. And so now I don't even have to deal with plugging in e to the I j omegas. I can just use the complex impedance and get the exact same result that I've got from before. I can use this idea quite easily and just sort of switch the components. Now you remember when we analyzed this with sines and cosines, we had to go through the analysis and remembering all our trig identities and whatnot. Now I use the exact same analysis that I had from the previous page. Now I just have 2 impedances in series, so I don't even have to redo the analysis. I can just immediately go to my relationship for the voltage divider, which is V out over Vn is equal to Z2 over Z1 plus Z2. But now I just have to plug in what my impedances were. So now Z2 is a resistor R, Z1 is a capacitor, 1 over j omega c, and Z2 is a resistor, and so that's equal. RC omega j over 1 plus RC omega j. And if you recall, when we analyzed this circuit before and we did this in lab, this was a high-pass filter. And as RC omega goes big, so to infinity, where this is sort of the dominant thing, then V out over Vn goes to 1. And as we go to low frequencies, so RC omega goes to 0, then we see that this term goes away, and V out over Vn goes to RC omega j. So now we see that rather than using sines and cosines and remembering trig identities or plugging in e to the j omega t's and doing lots of manipulations, we can just go straight to the impedance idea, redraw our circuit of resistors and capacitors with impedance, use all the laws we know for resistors, and then just sort of plug in the impedances at the end, and we get the immediate result, which will be a complex number. And that complex number will have embedded in it both the amplitude and the phase of the output signal relative to the input. So this is a super powerful idea, makes the analysis of these types of circuits very easy compared to what we have done before. One just has to sort of get over the mental hurdle that we're using imaginary numbers to represent things like capacitors and signals such as voltages and currents. But hopefully I've convinced you that it is equivalent and it is easier.